Hello everybody, and welcome to another lecture of 6838. Today we're going to be talking about a topic that's probably already familiar to many of you from the machine learning world, and that's the problem of clustering, or sometimes in computer graphics, computer vision, we call it segmentation. This is a problem that's really classic in unsupervised machine learning. It's one of the very first things that you learn about. But today we're going to try and put a bit of a geometric spin on this problem and show how a geometric perspective reveals lots of different ways to derive clustering and segmentation algorithms and also to extend them in an interesting fashion. So first of all, this lecture is titled Clustering and Segmentation, and that's because these are two terms that show up all over the place in the machine learning computer vision literature. One question that I asked is, what exactly is the difference between clustering and segmentation? And in my mind, these are very similar. I found this text in sort of business-oriented, I think a textbook actually, on segmentation is the process of putting customers into groups based on similarities, and clustering is the process of finding similarities in customers so that they can be grouped and therefore segment. I'll be honest, I don't know what this means, but we're going to use these terms pretty much interchangeably today. And I think that's pretty much reflected in the literature as well. So our objective today, rather than segmenting customers into different customer bases or whatever, is to take a piece of geometry and divide it into useful pieces. And this is the kind of problem that shows up all over the place. And of course, when I use phrases like geometric domain, hopefully by now in 6838, you've noticed that this phrase can mean many different things to many different people, right? It might mean a three-dimensional surface, it might mean a data set, and both of these things can be described using equally nice geometric language. Now, clustering and segmentation problems show up just about everywhere. Here I've given you a small sample of some of the contexts where we see clustering and segmentation. So for example, in unsupervised machine learning, I think just about everybody has heard of the k-means or EM algorithms, which are basically algorithms that take a big data set and then try to identify interesting clusters within that data set, in some sense to simplify it or kind of figure out what are the prototypical data points that summarize what's going on. In computer-aided design, sometimes clustering segmentation shows up. So for instance, on the upper right, we see a fan disk, which I believe is a part of a car, but it's also just a 3D model that we all know and love in computer graphics. But in any event, here they've segmented the fan disk surface into, I think, surfaces that are basically developable, like they can be manufactured out of long sheets. These are also sort of segments of the surface that probably are easily converted into CAD representation. In medical imaging, segmentation is really critical. So for example, one of the basic tasks that people do is to try and find functional regions on a brain surface or other pieces of anatomy. And then essentially once we have those different labeled parts, we can analyze their differences, their similarities, how they change over time, and so on. And then finally, for example, in computer graphics, we can use segmentation tools. In this case, tools that take in a 3D surface and break them into their constituent parts in order to do things like 3D matching and 3D modeling, where essentially we're mixing and matching different parts. So maybe I observe a big data set of 3D humans, and now I want to make my own human character that has arms like this guy's arms and legs like this other person's legs, and so on. Sort of make 3D characters in some Frankenstein fashion. That sounds a little bit grotesque, but the reality is that 3D modeling tools guided by AI more or less are doing precisely that, right? They're just looking at a data set of 3D models, and then when you make a new object, kind of building the new object by inferring some interesting information from the old ones. Now, it should probably occur to you by now that the clustering and segmentation problems are extremely, extremely general, right? I mean, you can see they show up all over the place in different applications. And so the sort of prototypical question that you probably should be asking when you start developing an algorithm for one of these tasks is, what does it even mean to be successful? In other words, what is a good segmentation? How do I know if I've succeeded at this task? Now, I've asked you a lot of questions of this nature throughout this course. For example, do I expect there to be a good optimization algorithm that applies to every possible objective I can think of? And almost always the answer is that, well, the question itself is sort of ill-posed. And I really do think that that's the case here, that essentially what makes a good segmentation completely depends on your application. Breaking bunnies apart is very different from identifying interesting clusters inside of a data set, and there's really no reason why one algorithm should apply equally well to both of those tasks. That said, many of us, including myself, were guilty in the early 2000s of working really hard on just generic algorithms for segmentation, sort of thinking of it as an end in itself. And so there's a whole literature of algorithms that are basically just high-level strategies for solving these problems. And even though I have contributed personally to that literature, my basic unsolicited advice to you all would be to be a little bit suspicious. In particular, again, segmentation isn't an end in itself. It's sort of a step in a larger data analysis pipeline. And really, I don't think it makes sense to say, like, this algorithm is just, k-means is always better than EM or something like that. You really have to understand the context, the data, the noise that you have, the geometric structure, and so on before you can make an informed decision. So as usual in this course, I'm going to waffle and tell you to try lots of tools rather than to tell you which thing is best. But that's just life in the city, in the engineering world. And in fact, the community slowly started to realize this over time. I actually found kind of a funny explanation of some of these challenges in a Facebook post from one of my colleagues, Aaron Hertzman. Hopefully he's okay that I screenshotted it. But one of the places where this sort of vagueness of these segmentation problems comes up is this overuse of the word semantic, which shows up a lot in computer vision. And somehow semantic is this placeholder that we often use for, like, semantic segmentation is taking a surface or an image and dividing it into, semantically meaningful parts. But the term semantic here is used by computer scientists, including myself, who often don't really understand what it means or where it came from. So Aaron and myself and the other people who like this Facebook post all would encourage you instead to, be a little bit more specific about your algorithm, a segmentation algorithm for this. Rather than finding semantically meaningful parts, say, I'm trying to find the arms and legs of a human or something. And that really helps us understand what you're doing. Now, that said, if you like working on segmentation problems, there's a huge number of different data sets out there that you can test on. And it's perfectly fine to perform well on one and not on another. So if you like these sorts of problems, essentially unsupervised machine learning problems in some sense, there's a vast literature of basically benchmarks that you can use to test your favorite heuristics and algorithms for segmentation, clustering, and related tasks, and basically understand if and how they're applicable to different application areas, whether it's medical imaging or gene sequencing, brain tumor identification, 3D mesh segmentation, video segmentation. These are all different problems. So, of course, we're not going to talk at this level of generality too much in 6838, but instead we're going to focus on a few interesting geometric methods for segmentation or clustering. And these really are, in some sense, going to be pretty generic algorithms, but they're basically taking, a piece of geometry and dividing it into meaningful parts. Now we're going to call out just a few of the many, many algorithms that are in this space. So we're going to focus on techniques that are sort of derivatives of the k-means algorithm, but out there in data science and 3D geometry and other places, there are many other approaches like mean shift, DB scan was another popular one that's reused a lot, especially in the sort of KDD community, and so on. So I encourage you all to read about these things at home and learn about just the breadth of different algorithms that exist for clustering segmentation problems. Now here, when I talk about geometric methods for these tasks, as always, our geometry can come from any number of places, whether it's the embedding of a data set, we even talked about different embedding algorithms if we don't have one available, the structure of a surface mesh, maybe you even apply a metric learning algorithm to your data and then try to cluster it. There are many different sources of geometric structure, and all of them are equally valuable and interesting. Well, maybe not equally interesting, but, Okay, so we're going to start with the clustering algorithm that everybody starts with when you talk about clustering. And that is a particular technique known as k-means clustering. Oops, Oh boy. So k-means clustering, here I'm showing you the image of k-means from Wikipedia, which I'm realizing is not particularly illustrative, but the basic point of k-means clustering is to search for, well, k-means. So the basic sets of variables, at least in the fashion that I have chosen to write this problem, are a bunch of points mu I and a bunch of sets s sub I. So here's the basic point. Let's say that I have a data set, and maybe my data set, I'm going to draw it in a fashion that makes it really obvious what the solution to my k-means problem should be. Like here are 3 clusters of data, and maybe in fact I get really lucky and I choose k equals 3. We're going to return in a little while to like, how did you actually choose k? So the k-means problem says that, okay, what I'm going to do is search for 3 sort of representative points that in some sense are summarizing my data set. So if k equals 3, then, and you know, here I'm in the 2-dimensional plane, right? Then essentially my unknowns in this problem are going to look like mu1, mu2, and mu3, which are all points in the plane. And essentially, I can think of them as the cluster centers. So for example, in an ideal universe, I'd probably place mu1 somewhere over here. I'd place mu2 somewhere over here. And I'd place mu3 somewhere over there. So that's the variable mu. And usually we call these the cluster centers. And then the other thing that we have to optimize for are the clusters. And now the cluster is basically S sub I, which is going to be some subset of my data set for I. So, right, so S sub I is a subset of my data set. So, I don't know, maybe I have big N data points, where I can think of cluster S sub I as all of the points which are closer to, you know, cluster center I than to any of the other ones, right? So here, I is going to go from 1 to k. So the basic idea here is that, like, I'm going to take my data and divide it into 3 groups, right? Like S1, S2, and S3. And each of those groups is associated with a mean, mu1, mu2, and mu3. And then the cost of my clustering, like this choice of variables, is this double sum, which I'm giving you on the slide here. So the outer sum is over every cluster center, right? So it's like the sum from 1 to 2 to 3. And then the inner sum is over all of the data points in SI. The basic point here being that essentially what I'm going to do is the cost of assigning a data point to set I is equal to the distance from that data point to the cluster center. Now, a simple calculus exercise actually shows that you don't really need both variables here. For example, I can write mu I is basically just 1 over the size of my set SI times the sum x in SI. And similarly, I can figure out SI as just the set of points that are closer to mu I than to any of the other centers. Right, so, you know, I can think of there being 2 variables, or I can think of there being 1. Doesn't really matter. Except that the way that I've written this problem here suggests a really simple algorithm, which is one that I'm guessing many people in this course have even implemented at home. And I think when we talk about k-means, we typically think of not just this model that I've written on the slide, where I'm summarizing my data with k points, and I'm assigning each data point to one of those k centers. But we're also thinking of a very specific algorithm which basically alternates between optimizing the s's and optimizing the mu's. So what do we end up doing? Well, if you think about it, if I hold the mu's constant and I optimize for the s's, oh, by the way, I guess I need a constraint here. I didn't actually write it, but whatever. The union from I equals 1 to k of my set SI is equal to the whole data set, right? Like that. Okay, but in any event, the k-means algorithm ping-pongs back and forth between two different steps, right? The first thing it can do is optimize the s's with the mu's fixed. And basically, one thing that you can see is that if you want to make the objective function as small as possible and the mu's are held constant, right? Well, what do I want to do? Essentially, I have the option of putting each of my data points into each of these sets. So, the cost of putting it into S1 is the distance squared to mu1. The cost of putting my data point into S3, for example, would be the distance squared to mu3. And the cost of putting a data point into S2 would be the distance squared to mu2. And if you think about it for a minute, then the obvious thing I should do is assign my data point to its closest cluster center, which is what's reflected here. That actually implicitly is defining something called a Voronoi diagram, which is sort of the partition of the plane into the sets of points that are closest to each of the mu i's relative to all the other ones. So anyway, that's how we optimize SI with the x's fixed. Then the next thing we have to do is hold the SI's fixed and find the mu i's. And you can do that by just taking the gradient, setting it equal to 0 with respect to x. I'm going to let you do that at home, and what you're going to find is just that mu I is the average of all the points, which kind of makes sense, right? Like essentially what it's saying is I've now labeled, like for instance, these 5 points as comprising the first cluster. And the question is, well, what point is the most central in that cluster? And it turns out to be the average, which I think we all would have expected. Now, one nice way to sort of view what's going on is you can think of the cluster centers as sort of the black points in this picture. And then the set S, they're determined by computing this object called a Voronoi diagram. So here, every colored region is what we would call a cell in the Voronoi diagram, and it comprises of all the points, in this case in the plane, that are closer to that one black point than to any of the others. The Voronoi diagram has all kinds of nice properties. If you take a classical geometry algorithms class, you spend quite a bit of time like constructing Voronoi diagrams in the plane and so on. But for purposes of understanding k-means, the basic point here is just that you can think of the SIs as basically Voronoi diagrams intersected with the data set. Now, here's an example of k-means clustering kind of in action. Let's see if I can play the video courtesy of YouTube here. Where'd my mouse go? Oops. Oh no. I practiced this at home. That's okay. So you all can download the slides at home and give that video a play. And what you'll see is that the cluster centers are basically just shifting around until they settle on some nice clustering. Sorry about that. Okay, so let's erase. Okay. So the k-means algorithm has an obvious property. Now, basically what it's doing is it's just alternating back and forth between optimizing the mu's with the s's fixes and then optimizing the s's with the mu's fixed. So you can convince yourself that this sort of Gauss-Seidel algorithm has to decrease the objective function in every step. That much is clear. And in fact, you can even sort of convince yourself that this algorithm will probably terminate at some point. But what you can't do is convince yourself that this algorithm will reach the global minimum of the objective function that I've put on the slide here. And in fact, k-means is famously prone to local optima, meaning that if I initialize my algorithm with different s's and mu's, it oftentimes will end up in very different clusterings of my data, which is problematic. So there's been a lot of research over the years in how to take k-means and make it more stable and less prone to local optima. Probably the most famous piece of research in this direction is a technique. I wish they didn't name it the way that they did because now it sounds the tiniest bit dated, but it's still, in some sense, state of the art, which is a technique called k-means plus plus. The idea here is that there's a randomized algorithm that you use for initializing k-means. And then once you do that, you can run the k-means algorithm to kind of refine your estimate and make it a little bit better. But actually, the theoretical guarantees that you get are from the initializer. The k-means algorithm itself isn't doing a whole lot. So the k-means plus plus algorithm is just a few extra lines of code beyond k-means. You all should implement it at home and play with it. Essentially, what it does is it's trying to come up with a relatively good initial guess of the set of k-means that you're going to then refine. So the way that it does that is that it chooses one mean of the k just uniformly at random for your data set. And now it iteratively follows the steps on the slide where you compute the distance from every point in your data set to its nearest neighbor in the k-means that you currently have. And you can construct a probability measure which on your data points, which is proportional to distance squared. So what does that mean? So like for instance, let's say that all of my data points happen to just be on the line here, and maybe they're like that. Right? So I have a data point at 1, 2, 3, 4, and 5. And initially I choose 1 as my first cluster center. Then what we're going to do is construct this distance squared function. So this is going to be, let's see, 0. The distance between the first data point and second is just 1. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And we're just going to normalize these things to sum to 1 so that it's a probability measure, right? So this is going to be, 16 plus 9 is 25, 6, 7, 8, 9, 30. So this will be 1/30th, 4/30th, 9/30th. I know we can simplify in 16/30th. So this defines a categorical distribution from which I can draw a point. And what do? Well, with high probability, I'm going to end up with a point that's far away from my first cluster center. And that's a good thing, right? So for instance, in 2 dimensions, if my data set looks like this, right? Maybe I randomly choose this point as my first point in k-means plus plus. Then with high probability, I want to choose a point that's far away, so it'll probably be over here. So maybe we choose, I don't know, this guy as our second cluster center. Then k-means just iterates this procedure, but now the probabilities that it chooses are proportional to distance squared to the closest point, right? So now actually everything is distance 1 to one of the cluster centers. So it's going to look like 0, 1/3, 1/3, 0, 1/3. And that's how you would choose the next one, and so on. So why do we like this k-means plus plus technique? Well, the basic reason is given in theorem 1.1 here, which is borrowed from the paper. The E on the left-hand side of the inequality here is an expectation. So the basic point is that what ends up happening is phi is the objective value of k-means, like what we've had on the last couple of slides. Then when you run this k-means plus plus randomized algorithm, then the expected value of the objective you're going to get for the initializer, right? Like this, the output of this procedure on the slide, is within basically a log factor of the global optimum. So that's pretty exciting because it actually says this algorithm as just even a replacement for k-means, if you just threw away step 5 here, already is giving you a pretty good estimate of the best set of k cluster centers. Notice that step 5, where you just call k-means clustering, basically only can decrease the objective function more because k-means is monotonic that way. So in any event, k-means plus plus was among the first of techniques to have any guarantee at all on performance for k-means. In fact, if you don't do something like this, then you can actually show that you can choose some really, really bad initial guesses for k-means that give you arbitrarily kind of yucky objective functions. The proof that this expectation is true, in other words, that if you run this randomized procedure with pretty high probability, you're going to get within a log factor of the global optimum, really isn't that difficult. If you guys bug me, maybe I can record a short segment with the proof, but it didn't quite fit into today's lecture. But it's worth kind of going through. It's a nice little probabilistic argument. Okay, so k-means plus plus and a few others that showed up at roughly the same time basically was this sort of interesting toehold into carrying out k-means optimization with some kind of guarantee. Notice this isn't telling you that you're getting the global optimum. In fact, we'll see that that's NP-hard. But at least you're within a log factor. And remember that k is small. So really this log factor is not so humongous. Now, there are many other options that have appeared since then, and essentially they try to do one of two things, which is either to improve the constant of the k-means plus plus initializer. I think that's actually quite hard to do. Or they try to make k-means plus plus more efficient. Like notice that in order to construct that d squared probability distribution, I have to iterate over all of my data points and make an array of that size. So for example, this algorithm on the left is like k-means parallel parallel, I believe, that shows how to do this in a scalable fashion. And then just recently, on the right-hand side, there's some interesting algorithms that are efficient and make use of machinery from Markov chain Monte Carlo, which is really interesting and clever technique. So I'll encourage you guys to take a look at these papers, especially if you have some probability background. Now, k-means plus plus, or rather just k-means more generally, is one of these algorithms that just keeps giving in terms of all of the challenges and problems it has, even though everybody uses it. The one that we just mentioned was choosing a clever seed. There's another challenge, which is the choice of k in k-means. So in other words, how do I know how many or how many clusters are in my data? And that's a really big problem. Now people typically in data science, what do? They just choose a bunch of different k's. They kind of see which ones seem to explain their data okay. But of course, if you want to be more scientific, there is a literature out there on how to do it. One of them tries to basically formalize a technique that is very popular among data scientists that they call the elbow method. The basic idea here is that you look at the variance explained by the set of clusters you get out of k-means. So like, for instance, if I have two very small or kind of tightly packed clusters, if I think of this as one data set that I explain with one Gaussian distribution, it'll actually have a pretty wide variance. But if I find two clusters, they actually both have two small variances. So maybe you can kind of use that observation to, look at where the variance really drops quickly per cluster. But formalizing that took a little bit longer. There's an extremely famous technique known as the Gap Statistic, which I've given you a pointer to the literature on this slide here, which computes a pretty easily computed number. So the basic point here is that you look at the variance going on inside of every cluster, which is roughly this quantity di, right? This is like the sum of pairwise squared distances between all the points in our different clusters, which are the SIs. And then WK here is basically just the average of these, or the sum of them normalized by their size. So the Gap statistic kind of compares the log of the variance that you observe in your clustering with the log of the variance that you observe in just like a random clustering. So they come up with a null model where you generate a new data set of endpoints, but your new data set doesn't necessarily have a cluster structure. So for example, maybe you do principal component analysis on your data set, and then you just like draw from a Gaussian as your null model. That's what this En star is representing. And then you compare the sort of average cluster variance in that thing to the cluster variance you got when you ran k-means, and sort of choose the one with the biggest difference as a function of k. So in any event, there's a huge amount of sort of data science interesting articles out there that try to explain this Gap statistic. There's also some nice probabilistic sort of analysis that is in the original paper and some of the follow-ups that I encourage you to give a close read to. Okay, so k-means applications show up just about everywhere, and that includes in graphics and vision, by the way. So for example, let's say I want to do image compression in a sort of old school way. One thing that I can do is maybe take the set of all the colors that I observe in an image and restrict it to a small palette by doing k-means on the set of colors. So like a bunch of RGB data points. And of course, this compresses quite a bit because now like you only need to store basically a reference into an array of size k in order to share your image pixels, rather than a full RGB value per pixel, which is a much more expensive thing to store. So this would be like kind of a dithering application. Or you could apply k-means not just to the embedding of your data directly, but also to features. So for example, one of the early algorithms for mesh segmentation, like taking a 3D model and dividing it into pieces, basically takes the mesh, maps it into, in this case, the GPS descriptor space. right? So if you recall from our lectures on the Laplacian, essentially it's associating every vertex on the mesh with a different point in a very high-dimensional space, which is meaningful geometrically, and then does clustering up there with k-means. And one of the interesting observations, which is somewhat empirical and somewhat mathematical, is that these actually descend to useful segmentations of 3D surfaces that are stable under deformation. Now, there's also an interesting research paper that I thought I'd point you guys to that does something a little bit different than like k-means plus and seeding, which is to sort of embrace the bug of k-means. So remember that k-means algorithm is unpredictable. It has lots of local optima, and depending on the way that you initialize it, you can get different segmentations. There's a really clever algorithm that was proposed in 2008 called Randomized Cuts for 3D surface analysis, where they say, okay, well, in some sense, what this gives us is a whole ensemble of different ways that I could segment my domain into interesting pieces. So I'm going to run k-means a bunch of times with different seeds, look at that collection, and then try to come up with an algorithm that summarizes it or finds the most stable cuts. And one of the interesting observations is that this randomized cuts technique that basically tries to summarize lots of clusterings that you just run over and over and over again. So someone was trying to find like the clusters on a surface, in this case, that are the most stable, leads to meaningful and stable results. Okay, so that's the k-means algorithm. Essentially, you're looking for k cluster centers. You assign every data point to its closest cluster center. You can optimize, and that's our basic model. Now, there's an interesting extension of k-means, which is applied in actually some literature related to a past lecture that we had in this course. And that is k-means where I add an additional constraint, namely that each set S sub I has to be the same size. So this is called balanced k-means sometimes. And I thought just for fun I would highlight that it's actually connected to our lecture on optimal transport. So in particular, we very briefly mentioned a particular model for optimal transport called semi-discrete transport. And in semi-discrete transport, we're trying to solve the transport problem between one probability measure, which is composed of just a few finite points, like the red thing, and then another probability measure, like the blue guy, that I can't say a whole lot about. And if you think about it, my transport map basically prescribes the amount of stuff that's assigned to each of the red arrows, right? And it's like the height of the arrow or the weight in front of the delta function in the equation that we had at the top. So I can actually interpret the k-means model as minimizing, it turns out, the Wasserstein distance between my data set represented as a measure and a smaller measure composed of k points. In particular, it looks something like this. So I can summarize my data set as follows. I can think of my data set, if it's composed of a bunch of points like x1 to x big N, then I can write it as a probability measure by doing the following. I can do 1 over big N times the sum over I of a delta function at each I, where I goes from 1 to N. Maybe let's call this measure nu. Okay, so nu is like a probability distribution with 1 over N amount of mass on each of my data points. Then I can actually understand k-means as the following, which is optimizing for a bunch of cluster centers. So let's say that I have, remember, mu1 to mu k. And now I can think of there being another number, in this case, which is like the proportion of points assigned to each cluster center. So the mu's are going to be, in my domain. I'm going to think of a1 to ak as just being positive numbers. In fact, that's a sum to 1, I guess. And I can minimize the Wasserstein distance between our nu. This is just a fixed constant probability measure, and then one that I've constructed out of my cluster centers. So maybe the sum of I equals 1 to k of ai delta xi. And you can actually convince yourself that this optimization problem here, this is precisely k-means. So if you wanted balanced k-means, then essentially you want to prescribe that every single cluster ends up being the same size. And the variable in this problem, which is controlling the cluster size, is the coefficient A, right? Because that's sort of like the mass associated with this delta function. So one thing that you can do is write a different optimization problem, which is just over cluster centers, like this, which is minimizing, again, the Wasserstein distance from our optimal transport lecture. But now I'm just going to say that there's a probability measure with 1 over k mass at each of my xi's. And this problem is balanced k-means. Because what I can't do in balanced k-means that I can do in this problem with these additional a variables is assign more points to one of the x's than to another. Now every single x has to receive the same amount of mass. Now in order to solve a problem like this, it turns out that what we need, and I'm just giving you Google search terms right now, we're not doing this in any detail. The Google search term you need here is something called a Laguerre cell, which cuts out a power diagram. This is opposed to a Voronoi cell in a Voronoi diagram. And basically the Laguerre cells are defined like Voronoi cells, but there's an additional set of parameters phi which bias the distance function. So basically what you're going to end up doing is you say, okay, each of my cluster centers, like these xi, oh sorry, this should be mu's. I apologize. Mu I. Don't love this notation because we usually use mu for probability measure in optimal transport. In fact, that's what I've written on the slide here, so I apologize for a bit of a clash here. Like these mu's are points and these mu's are probabilities, but bear with me. Right, so the Laguerre diagram is just like the power diagram. It's just like the Voronoi diagram, but I can make the cells bigger or smaller. And the way that I do that is by biasing the distance function. So that's what these phi's do. Essentially, the point of a Laguerre cell is that it looks for all points which are closer to xi than to xj, just like before. But when I say closer, I get to subtract off this phi I from each distance function. And the reason why this is useful is in the Laguerre diagram, I can make cells bigger or smaller until each one contains basically n divided by k points here, right? Because at the end of the day, in the balanced k-means problem, I need n over k points to each mu I, right? So I no longer get to make maybe in the original k-means problem, one cluster gets 1 point, another cluster gets 100 points or something like that. So this problem has a lot of different names. A different one is that it's the measure quantization problem. Essentially, the point here is that I'm going to take my original data set as a probability measure and quantize it on k points. Notice actually this problem is also well defined when mu is a smooth measure, like a mixture of Gaussians. But then it becomes a little harder to solve. Now, I think I'll omit it because I've already made a bit of a hash of this story, but there are algorithms for solving this optimal transport problem. Essentially, what they end up doing is basically modifying k-means in an interesting way. So here I've pointed you toward one stochastic technique that does that, where essentially you go back and forth between updating, in this case, the size of the cells in the power diagram. That's kind of like our replacement for the assignment step in k-means. And then, updating the cluster centers, which are just like before, basically the average data point inside of, in this case, the Laguerre cell. And there's even some interesting applications of these sorts of techniques in low dimensions to graphics problems. So, for instance, if I have a grayscale image and I'd like to approximate it with a sort of a stippling or what people call blue noise, like a well-distributed set of points, like what you see on the slide here. Well, now, in the this bad notation I've written on the board here, these cluster centers are kind of like the points that are composing our zebra here. And the new here is the original input image. And you want these things to be close in the transport distance. And this is kind of like k-means, but now, once again, I'm thinking of sort of taking the ink in my grayscale image and concentrating it at this set of points, which is what's leading us to this balanced condition. In any event, basically, measure quantization and balanced k-means are just extensions of k-means where you have an additional constraint that every single mean has to be assigned the same number of points, or that you kind of know the proportionality ahead of time. And these are really interesting problems. They're linked to our optimal transport lecture. It's definitely worth a read and to think about some more. So anyway, let's step back and think about the k-means algorithm a little bit more generally and cast it in, again, another geometric perspective. So in particular, k-means ping-pongs between these two steps, right? It does assignment and it does an update. And essentially, one of the interesting observations you can make is that these two steps don't have to happen in a Euclidean space, right? Notice I've highlighted these words closest and average. And basically, anytime we have a metric structure like a distance, we can find closest points. They don't have to be on Rn. So the only thing that we're missing is how to average them to complete our k-means alternation. So essentially, what we'd like is to be able to carry out k-means for points in a metric space. In order to do that, we just need a means of taking a mean. So in other words, this leads us to a really fun question to think about, not just in k-means, but in general, actually, which is, what does it mean to average a bunch of points that are on a curved domain? This shows up all over the place. Like, you know, oftentimes maybe you get a sample of a probability measure on a sphere, like you're, you know, getting camera motion as it's, you know, wiggling around or something like that, and you want to compute an average. It turns out there's a huge literature on this problem, and I thought I'd give you a few pointers into this. In particular, sort of the principal way that people compute averages in curved spaces is by computing something called a Frechet mean. Sometimes this is also called a Karcher mean. I believe there's a quote from Karcher saying that like he doesn't like that they call it a Karcher mean. But in any event, the basic point of Frechet means or Karcher means is just that they solve this optimization problem here. So the point is that if I have a distance metric d, then the Frechet mean of a set of points xi is the point p that minimizes the sum of squared distances to each of the xi's. And let's really quickly prove that this generalizes the Euclidean notion, or notation in my slide, of what it means to be a mean. So in particular, let's solve this optimization problem I've written on the upper right, which is basically the version of this problem that I just wrote down, specifically when I plug in the Euclidean distance. You can see here that there's a bunch of squared Euclidean terms. So how do I do that? Well, I take the gradient and set it equal to 0, in this case with respect to p, right? So this is the sum from I equals 1 to my number of data points, p minus xi. Okay, well, the gradient goes into the sum. And remember, this is the dot product between p minus xi and itself. So what you end up getting, let's see here. If I want to differentiate with respect to p is just 2p minus xi. Okay, so if I split out the sum, then I get 2n times the sum equals 1 to n of, I'm sorry. This is just, the first term is 2np. I shouldn't film these things at midnight. And then the second one is 2 times the sum from I equals 1 to big N of xi. So in other words, we get that p is equal to 1 over n, sum I equals 1 to n of xi. So what did we do? We just showed that if I solve this optimization problem on the upper right for p, then this basically just gives me the average. But the nice thing is that this definition of average generalizes to any metric space, right? Essentially, all I have to do is substitute in, instead of the norm of p minus xi squared, just a general distance p xi squared. And now suddenly I have a notion of average, like the Frechet mean, that works in any geometric space with some assumption. So for example, one very simple geometric space that we can think about is the set of positive numbers. So here, I put 2 pluses because I want to make sure that they're positive and not just non-negative. So I'm thinking of r plus as a set of x greater than 0. Okay, and I can put a distance metric on this space pretty easily. So in particular, positive numbers have logs, right? So I can write d of x comma y is equal to the absolute value of log x minus log y. Just for fun to do a quick example. So there's actually an isometric embedding of the real numbers into this space, which is really simple, right? So essentially, if I just take, I don't know, t and map it into e to the t, right? This gives me an isometry of r, like just the real numbers with the Euclidean norm distance into this new space r plus plus and d. One thing that's pretty clear is that isometries preserve Karcher means. And so, in fact, I can write Frechet means in this space. Okay, if I want to compute, I don't know, the Frechet mean of a set xi like that, I equals 1 to n. Well, one thing I can do is compute the Frechet mean in the pre-image space, which we just showed as the average, and then map it back because they're preserved under isometry. So in particular, what I'll get is, well, to map it back, I'll have the exponent, then I have 1 over n. The Frechet mean on the left-hand side is just an average. But I need to apply the map the other way, like that. And this is, of course, the same as the product I equals 1 to n of xi, all that to the 1 over n power, which is the geometric mean. So anyway, in case you were wondering, the geometric mean, oh, not meat. Your instructor's kind of hungry. The geometric mean, which is essentially, so the geometric mean can be understood as the Frechet mean of a bunch of positive values in the metric space where you're computing distances between log. So anyway, fun fact of the day here. Right. So there are all kinds of fun Frechet means that people compute in practice. For example, you can actually compute Frechet means of probability measures under the optimal transport distance to connect to a past lecture here. So if I make a bunch of probability measures concentrated on pairs of circles, like just basically little images in the plane of 2 ellipses, well, if I average all these images, they don't overlap geometrically, so I just get this weird mess like what's on the left-hand side. That's the Euclidean barycenter. So in other words, you're just kind of averaging every single pixel color independently. But if I do optimal transport in the image space, so it's allowed to kind of shift the circles around, I get this beautiful pair of rings on the right-hand side. This is a really beautiful example of what can happen in these barycenter problems. By the way, barycenter, I'm sorry, is another sort of synonym for Frechet mean. Nothing too special there. And in fact, actually, just recently, people have managed to differentiate through the Frechet mean operation, specifically, I think, in hyperbolic spaces, which are popular in machine learning problems, and applied them to different interesting neural networks. So this paper just appeared not so long ago. I'll encourage you guys to give it a read and see some of the interesting applications there. Now, all of these different algorithms have all kinds of fun extensions. So Lloyd's algorithm is sort of one other example of a k-means-like algorithm that basically is alternating back and forth between some averaging step and some clustering step. So for example, it's applied in this variational shape approximation research paper back from 2004 to sort of find patches along a surface that can be explained or approximated with very simple primitives like planes or ellipses or what have you. And in the medical imaging literature, computing Frechet means is popular as a means of basically summarizing a big collection of diffeomorphisms or of pieces of geometry. So for example, maybe you take a bunch of 3D brains and you map them all to some average brain in the Frechet sense, where people will actually put metrics on the space of brain warpings. And this allows you to do not just k-means, right? Like if I wanted to separate out Alzheimer's patients from not, but also things like principal component analysis, basically in the tangent plane to my manifold. So hopefully you see the pattern here. We started with the k-means algorithm. We're making it more and more and more general, right? So for instance, by introducing a Frechet mean, we now can carry out k-means when our data points are not on just a Euclidean space. And in fact, on spaces where Frechet means don't work, like I need some conditions in order to make that Frechet mean optimization problem well posed, there's a different algorithm out there called k-medioids, which basically just replaces that update step with a different one where you essentially, instead of finding a cluster center, which may not be a data point, you just find the data point inside of a cluster, which minimizes that objective function. So in other words, you're essentially restricting the space of mu variables to the data set itself. This is kind of nice because now all you have to do is compute distance values. You don't have to do anything else. And k-medioids is often pretty effective and stable. So for instance, one of the interesting applications is in clustering in a shape collection. There are notions of Frechet means in the space of shapes, but they tend to be very hard to compute, expensive, and kind of unstable. But there are also very efficient ways to compare shapes. So if you can compute a distance between two shapes that kind of measures how similar they are, that immediately gives you a way to cluster a data set of 3D models. So for example, one distance between shapes is something called Gromov-Hausdorf Distance. This is a fun one. So here I'm thinking of a piece of geometry like a 3D surface as a metric space. So just some object that is accompanied by a distance function, like the geodesic distance. So if I have two surfaces, then they have two distance functions, like dx and dy here. And I can look at the set of maps from one into the other. So here, if I think of phi as a mapping from x into y, then I can measure the distortion of phi by looking for a pair of points x and x prime, so that if x gets mapped to y and x prime gets mapped to y prime, then essentially what I want is that the distance from x to x prime looks like the distance from y to y prime. That sentence is hard to parse, but hopefully this diagram kind of helps you out. Essentially, you want to preserve distances under phi. You want it to look like an isometry. So the Gromov-Hausdorf distance between metric spaces essentially looks for the mapping from one domain into another. I forget if you need to symmetrize it or not, but in any event. And then evaluates each mapping based on the worst possible distortion. And essentially, you can show that this actually has a distance metric structure. But now it is a metric on metric spaces, which is pretty crazy. But if you can come up with an algorithm that approximates Gromov-Hausdorf distance, you can do things like clustering in a shape collection by using k-medioids, which is pretty nice. Now, it turns out that Gromov-Hausdorf distance computation is NP-hard. It looks kind of like quadratic assignment. But there are efficient algorithms for approximating it in practice. And so, for instance, here's a research paper that essentially uses it to cluster a data set based on different types of shapes. So it puts them all in correspondence with one another using this particular distortion measure and then runs k-medioids to cluster them into different categories. Okay, so I think we've done k-means to death, but we should also mention some other algorithms, some of which are heuristic and some are theoretically justified. So for instance, one common strategy is called agglomerative clustering. Agglomerative clustering says I'm going to start with every data point in its own cluster, and I'm going to take sort of clusters that are close to each other and just glue them together until I'm left with the right number, and then I stop. So maybe I take things that are somehow easy to draw circles around and I glue them together. This can be useful, for example, if I want to approximate a horse with a cannon. No, but like here's one of the early algorithms for surface segmentation. Essentially said that like maybe I want to find a segmentation of a surface into parts that look like some library of basic primitives like cylinders and spheres. So this is a really easy agglomerative clustering technique where initially I think of every single point as in its own cluster, and now the cost of gluing two clusters together is basically like the expanse, the best fit sphere or cylinder to the union of those two sets of points. And the agglomerative clustering algorithm just keeps gluing together the ones where it's the cheapest to do that, and it turns out this is a pretty effective technique. Now, this is an algorithm that's hard to prove much about, this sort of bottom-up algorithm. A similarly popular but hard to prove anything about algorithm is flood fill, which basically starts from some seeds and then grows clusters outward. But this is also a perfectly reasonable technique and one that shows up a lot in practice. In fact, I've encountered flood fill a lot in our work on political redistricting. So one of the early papers that proposed essentially sampling in the space of political districts to obtain a baseline. So like I want to know, do the voting districts in Florida have more of a Republican leaning than like the average, or like a big ensemble of districting plans that I generate. One of the first papers to think about this problem essentially made a probability distribution over political districting plans by essentially randomizing, in some sense, the seeds in the flood fill process. Now, there's a lot more to it than that because they want their algorithm to be reflective of the political realities, and there's a lot of debatable aspects of that. But I encourage you to give this a read and a book chapter that my colleague Amy and I wrote to get an idea of where these clustering algorithms show up in kind of an unexpected statistical application. In any event, going back to things that are less controversial, especially in, 2021 here, there are many different techniques for clustering out there, and you can apply them to many different data sets. So a very typical thing to do might be, maybe I want to cluster the points on a surface, but rather than doing that, I take the surface, I lift it into some feature space like GPS, like we saw before, and then cluster there. And this allows us to come up with basically different clustering algorithms just by computing different features. And you can evaluate them on many different axes. So I've pointed you to an interesting survey back in 2006 that sort of lays out a bunch of different clustering segmentation style objective functions and why they might be useful or not. So here are some issues so far in the clustering algorithms we talked about, with the possible exception of k-means plus plus, which is that it's really hard to figure out whether we have a global optimum of our problem. Certainly global optimum. And the other is that we're not using local relationships between points. We're like summarizing things with cluster centers, which could be quite distant from some of our data points, rather than just kind of gluing things together by local kind of information, with the exception of the agglomerative clustering technique. Now, with regard to this first consideration, unfortunately, we're unlikely to make a ton of progress. In fact, k-means, even when you put assumptions on it, like planarity of your data points, is NP hard to extract the global optimum. So in some sense, algorithms like k-means plus plus, which are randomized and in expectation do pretty well, are about as good as we can expect. But we can come up with algorithms that have some notion of global optimality, and also you can actually prove something about their approximation bound in practice, and that just make use of local relationships between points. And one example of that that's really popular in the literature is something called spectral clustering. In spectral clustering, you see that spectral word, you're going to get nervous, you talk about Laplace operators again, and you're right. Essentially has some rough notion of being globally optimal, which is kind of nice. Like k-means certainly doesn't have that. And it's deterministic. Like every time I run global clustering, spectral clustering, I get the same result. And moreover, it's able to assemble local relationships between points. So for instance, if you look at this data set here with these two concentric circles, well, k-means, what does it do? It basically, if k is equal to 2, it has to place 2 points on the plane that separate my data. And in this case, at least without a kernel, I'm unable to do that, right? All I can do is draw a straight line down the circle. In spectral clustering, essentially what it's going to do is cluster points by just looking at their local neighborhoods and then, kind of following relationships outward. So it's able, for example, to distinguish the inner part of the circle from the outer part. So what I thought we would talk about is one particularly popular model called Normalized Cuts, which does segmentation in a very different fashion. Now, in Normalized Cuts, as input, if we have n data points, then we're going to construct a matrix W, which is the pairwise similarity between our data points. Now here, the word similarity is one that you should take note of. Essentially, I want W to be big when I want, Wij should be big when data point I and data point J should be clustered together. Now, if I have distances, like my data point is in Euclidean space, how could I obtain W? Well, there's many different ways I could do it, right? I could take W to be 1 over distance, or e to the minus distance or something. So there are many choices. So basically, our job here is to cut our data, in this case, just into 2 segments. So let's say that I have, a data set, maybe it looks like this, right? So I've got data over here, data over there. And I'm trying to find 2 clusters, like here's A and here's B. Okay, so one thing that we can do is we can look at the score of a cut of our data into these 2 pieces, A and B. And what is the cut score? Well, essentially, we can think of it as like I'm trying to engineer an objective function that's going to be small when I've chosen a good pair of sets A and B. Well, what is a good clustering? Well, in some sense, remember that like here is my Wij, which is the weight associated with these 2 data points. And if I and J are in different clusters, well, then I want Wij to be small, right? Because I want clusters to be similar stuff and different clusters to be dissimilar stuff. So one very simple measure of how well my clustering of my data set into this bipartition AB is just to look at the sum of like all the W's that cross over my cut. And we can define that to be the cut score, C of AB, which you can write as just the sum where I'm going to choose I in A, J in B of Wij. And notice that this is large when I have a bad clustering and it's small when I have a good clustering, right? Because, it's small when essentially the points in A and the points in B are not similar to one another. Now, you'd be tempted to come up with an optimization algorithm for clustering that just tries to minimize C over bipartitions of my data. But that turns out to be a bad choice because of one obvious thing, which is, well, if I put all of my data in A and then make B empty, for example, well, then my cut score is 0 and I win, right? And so that's no good. By the way, we usually think of W as positive. So in other words, we have to make sure that we don't game the system by basically just putting everything into one cluster so that there just aren't that many edges that go across. And one way to do that is to normalize by volume. So we can think of volume of a set, like for example of A, is equal to the set, or rather the sum, where I'm going to choose I to be in my set A. And then in this particular model, I'm going to choose J to be any point, Wij. So this includes the similarities outside, it includes the similarities inside, but the basic point here is that the volume is somehow the amount of W-ness that's hiding inside of A. And then essentially, in order to get rid of this like sets of size 1 or 0 problem, rather than optimizing C, in the normalized cuts model, we optimize something called N, where N of A comma B is basically just going to be C with a scaling factor in front, next to it. So I can write C of A, B multiplied by the inverse volume of A plus the inverse volume of B. So the point here is that essentially, I don't just want the cut score to be small, I want the cut score relative to the volumes to be small. Now, there are many variations of this model. For instance, maybe I do 1 over the sum of the volumes instead of the sum of 1 over the volumes. Well, many of these have been published and analyzed in the literature, but I think this is the main model. So essentially, our goal in the normalized cuts algorithm is to optimize this score, in other words, to find the smallest possible partition of my data set into set A and set B to make this value small. Sorry, that sentence didn't quite parse. And let's see one technique that attempts to do so. So what we're going to do is we're going to make a definition which is given on the upper right corner of the screen here, which is here. I think I'm just going to box around it. So in particular, we're going to make kind of a funny way to encode a particular partition. So let's say that I have a candidate partition and I want to know how well I did. Then one thing that I can do is I can define a vector x with elements xi, where if I decided to put data point I into set A, then I'm going to set xi to be 1 over the volume of A. And if I put data point I into set B, I'm going to put it minus 1 over the volume of B. So again, what am I doing here? I have a data set, and I have a potential clustering into set A and set B. Then I can just define this weird vector of values x, which is written in this formula here. And what we're going to see is the normalized cut score basically it comes out looking really nice in terms of the elements of this vector x. Okay, so it is kind of an unnatural looking definition. I'll give it to you. I'll give that to you. But we're going to see that it makes our life a lot easier. So now that we've made, by the way, can we recover our partition into A and B from the vector x? Well, yes, right? Because essentially all the elements of x that are positive go into A, and all the elements of x that are negative go into B. So if I have x, I have our partition. If I have our partition, I can compute x. Okay, so here's what we're going to do. Now, one thing that I think we've found out a few times in this course is that least squares problems are easier than general optimization problems. So one thing that I can do is try to make the normalized cut score look a little bit more like least squares. So in particular, I'm going to compute a slightly different value, which is the cut of A comma B. But I'm going to screw up my normalization a tiny bit and then show how to fix it. So one thing I can do is multiply this by VA inverse plus VB inverse. But now what I'm going to do is square this value. Now, just bear with me for a minute that I can get rid of that square. And let's say that I wanted to approximate this number instead. This is a weird number to approximate, but bear with me. So one thing I can do is take the definition of C and just plug it in, right? So this is the sum of I in A and J in B of Wij times this coefficient here, right? VA inverse times VB inverse, like that. Okay, but here's something kind of funny. So take a look at the way that I basically designed my vector x. Right? When I is an A, well, then VA inverse is equal to xi. Well, in every term in the sum, by definition, I is an A. So if I want VA inverse, I can just write xi. And for every term in the sum, j is in B. Notice that when j is in B, xj is equal to minus the volume of b to the minus 1. So in other words, I have this expression here. Now you can probably see why I chose to put this little pesky, 2 here, right? It's not useful for normalized cuts, I'll give you that. We need to get rid of it. But this expression should look awfully familiar to you. This is a Dirichlet energy. Every time you try to get out, they pull you back in, right? And this is looking like a Laplacian. And in fact, it's almost like a Laplacian, except that we have these annoying I and A and J and B terms here. But what happens if I is an A and J is an A? Well, then xi and xj are both equal to VA inverse. And so their difference is 0. Similarly, if both I and j are in B, well, then both terms is equal to V of B inverse times minus 1. So in fact, this sum is exactly the same as the sum over all ij, wij xi minus xj squared. And essentially, to get from one to the other here, I just added a bunch of zeros. That's it. Okay, so now what is this expression? Well, this is just a quadratic form. It's symmetric in x. And so I can actually just write this as, hopefully you remember, this is a weighted graph Laplacian. So this is really x transpose Lx, where L is equal to D minus W, and D is a diagonal matrix where dii is equal to the sum over J of Wij. Now I'm going to let you guys check that you can get from here to here on your own at home because it's very close to the calculations we were doing on graph Laplacians. In fact, it's basically identical. Okay. So now you can see why this quantity is kind of interesting because it looks like a quadratic form in this weird vector x that I've defined for you. Mysterious. But there's a problem, which is that I squared this thing. That's not the normalization I wanted. I want just 1 over volume. I don't want 1 over volume squared. So I need to get rid of that square. So what do I need to do? I need to take this expression, x transpose Lx, and divide it by a quantity which is equal to VA inverse plus VB inverse. And in fact, I can do that. And this is just beautiful, this little observation. Like this funny vector x that I've defined here is kind of magical. In particular, just for fun, remember that like when we did the Laplacian, one thing we did a lot of was work with mass matrices, and somehow we have one staring at us right here. So let's compute, just for fun and profit, x transpose dx. Okay. Well, what is this? So remember that D is a diagonal matrix. So this is the sum over I of xii dii. I guess xii squared dii, sorry. Okay. And what is dii? Well, we can plug in our formula here. So this is the sum over I xii squared. And then dii is a sum over j, wij, like that. Okay. So what are we going to do? Well, one thing that we can do, which is kind of sneaky, is we can take this sum here. Remember that the sum is like a sum over our entire data set. And we're going to split it into 2 subsets, right? Into subset A and subset B. Right? Essentially, the sum over all I is equal to the sum over all I and A plus the sum over all I and B. Okay, so this is really sum over I in A of xii squared sum j wij plus the sum over I in B of xii squared sum over j wij. So all I did was take this sum and split it into 2 pieces. But now we're cooking with gas. Oh, oops, I'm sorry. There only needs to be 1 I index here. It's just xi, not xii. My apologies. Okay. Now, why do I do that? Well, remember our definition again of this x variable. Well, in particular, when I is in A, xi is equal to v of A inverse, right? So really, this expression is the sum over I in A of v of A inverse squared, so to the minus 2, sum over j wij, like that. And similarly here, this is plus sum I in B. Well, xi when I is in B is equal to minus v of B inverse, so this is v of B to the minus 2, sum over j wij. And so these guys are constants, so I can move them outside of the sums, like that. And what do I have? Well, I'm going to have the sum over I and A, sum of j wij. Well, that's exactly v of A. So what do I have? A v of A to the minus 2 times v of A. This is v of A to the minus 1. And similarly, this term here ends up being v of B to the minus 1. Aha! And that is how we're going to cancel this 2. So at the end of the day, what we proved is that we can write this really weird expression for our normalized cut score, which is that it's equal to x transpose Lx divided by x transpose dx. And this is a Rayleigh quotient. In other words, it's something we know how to optimize in our sort of eigenvalue theory. Okay, so here is a really weird version of our normalized cuts algorithm, or our normalized cuts problem, right? Remember that it's still a discrete optimization, right? Like we're still minimizing over A and B. Well, now I can write it as follows. So L and D here, these are just functions of our input matrix W. So like, it's perfectly fine to write X transpose LX divided by X transpose DX, like that. And we have such that X is equal to, you know, the definition that we've made up here. Okay. So here's the thing. This problem is no easier to solve than what I started with. I just wrote it in weird slick notation. Right now it's kind of looking like a quadratic form. But one thing that we do is we say, okay, this problem is still hard to solve. I mean, these are combinatorial variables, A and B here. So what I'm going to do is remove constraints to get an approximation. In other words, I'm going to relax our problem. And what I'm going to do is say, okay, this is an optimization over A, B, and in some sense X, with a very heavy-duty constraint linking them all together, and in particular, linking, making A and B combinatorial variables. But if I relax this problem and I start dropping constraints, I can write it as just a min over X of X transpose LX divided by X transpose DX. One thing that you can check, by the way, is that this X sums to 0. So I might as well add that condition. This gives me a lower bound for my original problem. Do you see that? Because I started with this problem and I removed constraints. And when I remove constraints from a minimization problem, the optimal objective decreases. Okay? So if you take the gradient of this Rayleigh quotient problem and you set it equal to 0, one thing you can check is that well, if I ignored this constraint, essentially what I'd get when I take gradient set it equal to 0 is, well, Lx equals the Lagrange multiplier times dx. This is the optimality criterion for the problem here without the constraint. But then it turns out that essentially there's a 0 eigenvalue in L. We know that because it's a Laplacian matrix. So essentially what we want is to find the first non-zero generalized eigenvalue of L comma D. And that, my friends, this is the normalized cuts model. So we started with this objective over here on the left-hand side, right? This is saying that I'd like to optimize the cut score, but there's a problem, which is that this score by itself just wants to put everything into one side of the cut. So I fixed that by normalizing about basically the size of the two cuts. Now I write this really funky version of this problem, which looks like the ratio of two quadratic forms. But really, that's a lie. I mean, like, I have this variable x, but I wrote x in terms of my combinatorial variables a and b using this weird definition on the right-hand side. So what do? Well, I relax. And essentially, I just optimize for x, forgetting that it came from a combinatorial problem. This is a very coarse relaxation, incidentally, but it is a relaxation nonetheless, so at least we know that we've lower bounded the optimal objective here. And essentially, the way that I do that is I just solve this eigenvalue problem. Lx equals lambda dx. Look for the first non-zero eigenvalue of this matrix. But there's a problem, which is the x I'm going to get, well, it doesn't end up actually being the clustering that I wanted, right? I relaxed my problem. So I need some heuristic for recovering. But remember that we can recover our clustering into A and B here by just looking at the sign. So at the end of the day, in the normalized cuts algorithm, what they end up doing is use the sign of each xi to determine which cluster it's in. So we did a bunch of math, but at the end of the day, implementing this algorithm is like 3 lines of code. Let's make sure that you see that. So what do? Remember that as input to your algorithm, you're given this similarity matrix W. So the actual code that you have to write constructs 2 matrices L and D out of W in closed form, just using the formulas here, and then puts those into an eigenvalue problem. Right? This is known as a generalized eigenvalue problem because there's a D on the right-hand side, but that turns out not to be a big deal. And then you just take the one lambda, which is closest to 0 but not exactly 0, and the corresponding x is the optimal x for this relaxed problem on the right-hand side. Now the only problem is that it's the optimal x for this relaxed problem. It's not the optimal x for our combinatorial problem, but our heuristic is that we just take all of the positive elements of x and put them in one cluster, and all the negative elements of x and put them in another. Okay, so that's our basic technique, and it's actually pretty straightforward to implement, even if the derivation, or at least the motivation here, is a little bit complicated. Okay, so let's clear up. So just incidentally, notice, by the way, that we started with yet another computational problem, in this case clustering, and ended up once again with a Laplacian operator and an eigenvalue problem to solve that gave us our clustering. So in this case, we computed the graph Laplacian corresponding to our similarity matrix W. We compute its eigenvectors, and essentially now we're using the sign of the first non-zero eigenvector as a way to compute our clustering. Right, and the problem just looked like this. So here's a nice example of this kind of a computation going on a k nearest neighbors graph. So here I think what we did is, what David Sontag did, is essentially construct a graph here by connecting every vertex to its k nearest neighbors. Looks like k is maybe 3-ish. And I think the similarity matrix is 1 when there's an edge and 0 when there's not. So when you do this calculation, in this case, you actually get the graph Laplacian for sure. That's why sometimes this is called graph clustering. And you can see that essentially the clustering you end up getting into red and blue here separates into 2 pretty meaningful parts. Now, one obvious question you should ask is, how do I take this technique and make it work for more than 2 clusters? And unfortunately, that turns out to be kind of tricky, which is a little disappointing, right? It turns out it's pretty easy to get a really stable, useful clustering into 2 pieces using normalized cuts, but then more than 2 gets to be a bit tricky. Here are 2 different ways that people do this in practice. One is called recursive bipartitioning, where essentially it's kind of like agglomerative clustering maybe. You know, like a very simple strategy would be split my data set into 2, split those things into 2 each, and so on. A different thing that I think is more popular to do in practice would be to compute more than 1 eigenvector of the Laplacian and then do k-means on that embedding. So this is kind of funny, right? Like essentially, you know, the k equals 2 case on the eigenvector, just the first eigenvector of the Laplacian, is exactly the normalized cuts algorithm. So here we're kind of combining normalized cuts and k-means in an interesting fashion. Incidentally, recall that the second smallest eigenvector of a graph or of a matrix like W really is a pretty meaningful object. It's called the Fiedler vector, or the algebraic connectivity, when it's associated to a graph. And we could have motivated the entire algorithm I wrote down, instead of using a general similarity matrix, just using a binary one, which is 1 when there's an edge in a graph. And what you get is a graph partitioning algorithm. Essentially, the volume now is going to kind of count edges in a graph that cross between clusters, which is totally natural and one of the kind of standard techniques for taking a network, like a social network, and dividing it into 2 pieces. In fact, the same technique is also used with the surface Laplacian to find interesting segments. So for instance, in this old computers and graphics paper, they basically propose using Laplacian eigenvectors plus this k-means tricks and so on to identify stable segments on a surface. In this case, what they use is not just the first eigenvector, which would like always cut every surface in half, but maybe a higher order eigenvector, and then to define it into regions where that eigenvector is positive and negative. These are called nodal, nodal domains of the Laplacian. I'm rushing because I'm at the end of the hour here. So essentially, yet another way to obtain a partition into more than two pieces would be to take an eigenvector which is even farther away from 0, so maybe not like the first or second eigenvector, but one corresponding to a larger eigenvalue. So that's going to oscillate more, right? And then we divide the surface into connected regions where the eigenfunction has a constant sign. And it turns out that's actually a sensible way to do clustering. So there's a theorem by Courant that essentially the kth eigenfunction has at most k nodal domains. It can have fewer, but at least that gives you some bound on the number of segments that you get depending on what eigenfunction you use. So in any event, that's spectral clustering, and basically the point here is that the Laplacian shows up one more time. So in this case, if I want to cluster a graph or a similarity matrix or whatever, what do? I construct the Laplacian, I compute its eigenvector, and I just cut based on the sign. And then there's some extensions of that to more than two regions. Now, very briefly at the end of the lecture today, I thought I'd mention some interesting additional problems to think about. There are many of them in clustering. So here are some examples. One is that essentially sometimes if you run the algorithms I've introduced for you so far, they're inconsistent, meaning that if I have sort of related 3D models, there's no reason why they would make the same segmentation, for example, on each one. So for example here, the 3D model on the right-hand side, she has pretty straight legs. So the knee is not an interesting feature, and the segmentation algorithm misses it. Whereas on the left model or in the middle, there are two segments for the upper leg and the lower leg because there's an interesting piece of geometry. And this leads to a broader question, which is like, is segmentation a purely geometric problem? The answer is no. Right? So for example, segmenting those humans, we know that there's a knee in the middle of your leg. And so you probably want to segment the upper leg and the lower leg in two different segments, even in the character on the right who doesn't have a prominent feature in the middle. So in fact, we really should be incorporating information that we know about our application. An even better example here is in segmenting the brain. Sure, geometry gives you a clue, but we also have many, many studies telling us what the interesting functional regions are. We shouldn't just do k-means on like a spectral feature or something. So what's been more popular recently are basically supervised learning techniques, for example, that take data sets of segmented models and then try to infer how to do the segmentation on a new input model. So there are many, 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 many algorithms that have appeared in the last decade for this problem. In fact, what's amazing to me is that this one that I'm highlighting here is already over 10 years old, and in some sense was one of the very first approaches to use machine learning. In this case, they use a conditional random field approach, which essentially takes a data set of 3D models and tries to infer a labeling per vertex from geometric features, but also incorporate some smoothness prior. At this point, we probably don't need to cover this paper in detail because it's been replaced many times over, but it is probably historically one of the first ones to consider machine learning for surface segmentation. But these days, this is just a model task in computer vision. And so later on in this course, we're going to talk about deep learning models that consider, for example, point clouds or meshes. And we'll see that consistent segmentation or just supervised segmentation is one of the classic test cases for these algorithms. Now, for whatever reason, there are very large data sets of 3D furniture, so we all test on these models. But you can see here that basically the supervised learning algorithm is able to separate, in this case, the legs from the seat from the backs of the chairs. The supervised technique, of course, has the drawback that you need a big data set of segmented models, which is often unavailable. So another thread is to think about unsupervised learning algorithms. For example, if I'm trying to find knees on humans, one thing I could do would be to map a human to another one which has a bent leg and notice that they have an interesting segment and then pull that back. So by having an entire shape collection, sometimes I can infer segments that I might not be able to infer from a single model. But we'll save that for our discussion of consistent correspondence. So that concludes our whirlwind introduction to clustering and segmentation. We started by introducing the k-means algorithm, which is efficient enough but prone to many local optima, some of which can be fixed by techniques like k-means++. We talked about extensions of k-means into metric spaces using Frechet means and similar constructions, or by using the k-medioids algorithm, which doesn't require computing an average. We talked about balanced k-means problems and measure quantization, and I briefly sketched out why it's relevant to optimal transport. I'll admit that part might have lost you because it went by fast. And then finally, we motivated the normalized cuts and more generally spectral segmentation algorithms, the spectral clustering, which basically build up a Laplacian matrix, compute its first eigenvector, and then use the sign of that eigenvector to cut between different segments. So this is a fun area. Hopefully you have some idea of the basic language that people use to describe algorithms in this space, and now you can go back and read more. In this part of our course, we rush through many different fun applied topics, and my basic goal here is just to give you a flavor of the way that these folks think, some of their basic techniques, and enough language that you can dig into these papers further. So with that, I'll see you next time.